Okay, in this video we'll be going through the 2015 Level 3 Waves exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you've finished the question or get stuck, unpause the video and see how I go about getting the answer. A shower acts as a closed pipe with nodes at both ends. Matthew's shower has a height of 2.4 meters with a square base of width 1.1 meters. The diagram shows the side view of the shower with one standing wave that can be set up in the shower. The displacement antinodes and nodes are shown in the diagram. Show that the frequency of the vertical standing wave is 71.5 Hz. Okay, so we know whenever we have a case where we have a closed pipe with nodes at both ends, our length is equal to 1/2 of the wavelength for the fundamental frequency that is. And therefore, as we know that our length is half a wavelength, 2 times our length is going to be 1 wavelength. We know that the length in this case is the height of the shower, because that is our length right there. And therefore 2 times 2.4 is equal to our wavelength, which means our wavelength is 4.8 meters. Now we know that V is equal to F lambda, and therefore F is equal to V all over our wavelength. We know that the velocity of the wave is 343 meters per second. Now, a thing that a lot of students mess up, and myself included when I was doing this past exam for my revision, is I thought that we were going to use the speed of sound of water because he's in a shower, right? That makes complete sense. But what this description doesn't tell you, and it tells us later on, is that this wave is produced by a speaker. It doesn't tell you that here, and so I also assumed that it was water, but in this case, because it's a speaker producing the wave, it's the speed of sound in air. Confusing, I know. So, plugging in our numbers, we get our frequency is the speed of sound on air, which is 343, all over our wavelength, which is 4.8, and that gives 71.46 Hz, which can be rounded to 71.5 Hz to 1 decimal place. And as you can see, that is the frequency that we're trying to find. Matthew loves singing in the shower. Although Matthew is a talented singer, he cannot sing a note to resonate at this lower frequency. However, Matthew can produce 2 resonant frequencies, a vertical standing wave of 143 Hz and a horizontal standing wave of 156 Hz. Draw these 2 standing waves in the box to the right. Show the calculations you used in order to draw these 2 waves. Again, we know V is equal to F lambda. What we want to do is find the wavelength of these 2 waves. And so we can get lambda is equal to V over F. Now again, we know that the speed of sound in air, in this case, is 343. Let's calculate the vertical one first, so that has a frequency of 143, and that's equal to 2.4 meters. And so what this tells us is that 1 wavelength can fit in the entire vertical space. So 1 whole wavelength can fit in that vertical space. Now we can do the same process for the horizontal, V over F. Again, velocity of the wave is 343 all over the frequency, which is 156, and that's equal to 2.2 meters. Now comparing that to the horizontal length is 1.1 meters. And so what we can gather from that is that only half a wavelength can fit in that space. And so what we do is we draw half a wavelength. One day, Matthew finds his shower is filling with water because the shower waste pipe is blocked. Matthew drains the water from the wastepipe and attempts to locate the position of the blockage. With a loudspeaker, Matthew detects the fundamental frequency and then detects the 2 adjacent resonant frequencies at 180 and 300 Hz. Matthew uses these resonant frequencies to estimate that the pipe is blocked 1.43 meters from open end. Show how Matthew calculated that the pipe is blocked 1.43 meters from the open end. You may want to draw waveforms in the diagram below to help you. So the main thing that these diagrams tell us is that this is a situation where we have an open end over here and a closed end over here, meaning that we have a node on this side and an antinode over here. We know in this case that the fundamental frequency has a wavelength that is 1/4 of the length. The next resonant frequency, which is the 3rd harmonic, at that point, the length is going to be 3/4 of the wavelength. And the next resonant frequency after that is going to be the 5th harmonic, and the length is going to be 5/4 of the wavelength. Now again, as you should know that this is the case because only odd number of quarter harmonics are allowed. So there are actually 3 ways when we can work out this problem. I'm going to walk you through all 3 because why not? The first way is to use this fundamental frequency. So in order to work out the fundamental frequency, we know that F3 is equal to 180 Hz, and we know that F5 is equal to 300 Hz. We get that information from right here. So in order to work out f1, which is our fundamental frequency, we can take f3 and divide it by 3, or we can take f5 and divide it by 5. So in both cases, if we take f3 and divide it by 3, which is 180 divided by 3, that's equal to 60 Hertz. Or if we take f5, which is 300 Hertz, divide that by 5, that's also 60 Hertz. So our fundamental frequency is 60 Hertz. From there, we can use V is equal to F lambda, and therefore lambda is equal to V over F. We know that the speed of sound is 343 all over our frequency of 60 Hertz, and that gives us a wavelength of 5.72 meters. We also know that at the fundamental frequency, the length is equal to 1/4 of the wavelength, and therefore L is equal to 1/4 of 5.72, and that is indeed 1.43 meters. And so that's one way in which we can get the answer. The other two ways use this information right here. So moving on to the second method, we know that the third resonant frequency is 180 Hertz, and so we can find the wavelength at that third resonant frequency. And so lambda is equal to V over F again, where our velocity is again still 343, all over our frequency, which is 180 Hertz, because that is the frequency of the third harmonic. And that gives a wavelength of 1.91 meters. Now again, we know that at that third resonant frequency, the length is equal to 3/4 of the wavelength, and so therefore, for L all over 3 is equal to our wavelength. And so therefore, L is equal to 3 over 4 times 1.91, and that gives a length of 1.43 meters. So that is our second way in which we can solve this problem. Now, the third and final way is pretty much the exact same as the second way, except we use the fifth resonant frequency instead. So we know our wavelength is equal to V over F, and so our velocity is, you guessed it, 343 all over our frequency, which is now 300 Hertz for the fifth resonant frequency, and that gives a length of 1.14 meters. Now, same thing, we know our length is equal to 5 over 4 times our wavelength, which is 1.14. And you guessed it, that indeed gives a length of 1.43 meters. There we go. So those are 3 different ways where we can solve this problem. The second and third way are definitely faster, but you can do what you want, really. With the loudspeaker still set to 300 Hertz, Matthew fills the waste pipe with water. He uses his loudspeaker to make sound waves in the water, and puts his ear in the water and listens, but the sound no longer resonates. Calculate one of the frequencies that Matthew should set the loudspeaker to in order to get it to resonate again. In your answer, you should describe how water affects the speed of sound in the wave, explain why the sound in the waste pipe no longer resonates at 300 Hertz, and calculate one of the resonant frequencies. Okay, so 300 Hertz is no longer the resonant frequency because the sound in the wave is now traveling faster. Speed of sound in air is 343 meters per second. However, speed of sound in water is 1.49 times 10 to the 3 meters per second. And we know that information from all the way back up here. Now, this is the exact same as saying 1,490 meters per second. I just like to do that because I hate writing times 10 to the something. I just feel like it takes forever to write, so I'm going to be writing it like this from now. Just know that they're the same value. So. Now, the reason why this increase in the speed of sound matters is because we know that frequency is directly proportional to the velocity of the wave. So if the velocity of the wave increases, the resonant frequencies would also increase. Now, at the speed of sound, that is 1,490. Now, if we use our frequency of 300 Hertz with a wave velocity of 1,490, we get a wavelength of 4.97 meters. Now, we know that the first fundamental frequency is, again, 1/4 of the wavelength, and so our length has to be 1/4 of 4.97, and that is equal to 1.24 meters. Should probably clean that up. There we go. Now, as we know from the previous questions, our length of our pipe is 1.43 meters, not 1.24, and so our pipe is too long, and so therefore, at 300 Hertz, the sound cannot resonate. So in order to find the resonant frequencies, we can use our F is equal to V all over our wavelength. Our velocity of the wave is, again, 1,490 because we're trying to find the resonant frequencies when the wave speed is the speed of sound in water. And that is all over our wavelength. Now for our wavelength, we know that L is equal to 1/4 of the wavelength. And so therefore, 4L is equal to our lambda. Now in this case, our length is 1.43, so 4 times 1.43 is equal to lambda, and this gives us a wavelength of 5.72 meters, which is the same value that we got up here. And so this wavelength will give us our fundamental frequency. And so if we put our wavelength as 5.72, this will give us our fundamental frequency of 260 hertz. There we go. Alright, question 2. Renee? Does that say Renee? I think it says Renee. If it isn't, too bad. She's Renee now. Renee uses a pair of novelty glasses to produce a laser show. When she shines the laser through the center of one of the eyepieces, the laser splits the light into a number of beams. She suspects that the novelty glasses contains a diffraction grating. Renee measures the angle between the bright central beam of light and the first order maximum in the horizontal direction to be 26 degrees. The laser light has a wavelength of 532 nanometers. Calculate the slit spacing of the novelty glasses. So this question is just a simple n lambda is equal to d sine theta question. We can set n is equal to 1 because we know that the angle between n is equal to 0 and n is equal to 1 is equal to 26 degrees. And so with n is equal to 1, we know that lambda is just equal to d sine theta now, because anything times 1 is just itself, so 1 times lambda is just lambda. And so now rearranging for d, lambda all over sine theta is equal to our d. We know our wavelength is 532 times 10 to the 9, all over sine theta, which is 26 degrees, and this gives us a d of 1.21 times 10 to the negative 6 meters. Renee experiments by shining her laser light through different parts of the glasses. There are more lines per meter in the middle of each eyepiece, smaller slit spacing, than there are at the edges. Describe the differences in the pattern Renee would see when she shines the laser through the two different sections of the glasses. Okay, so in the middle, it says that the slit spacing is smaller, and therefore each antinode, or each bright spot, is going to be further apart, which means that there's going to be less of them. Now at the edges, this is just the opposite, right? The antinodes, or again, the points of maximum, or the bright spots, or whatever you want to call them, are going to be closer together, and therefore there's going to be more of them. And based on that, you can write a beautiful answer. Again, you can't just write these bullet points. You have to write coherent sentences. Renee visits a laboratory where she replaces the novelty glasses with a 600,000 lines per meter diffraction gradient. Calculate the spacing in degrees between the central maximum and the second order maximum of her laser light when she passes it through the diffraction gradient. Okay, so first we need to calculate our d. Our d is equal to 1 over 600,000. A lot of students are confused on why we usually take the inverse. The way I thought of it back when I was doing level 3 is we have lines per meter. And so the dimension of lines per meter is n to the minus 1, right? Lines per meter. However, d has dimensions of just meter. And so if we want to take lines per meter to just meter, we can put it to the minus 1. And what that does is give you dimensions of meter. So that's how I like to think of it. And if that helps you, then yes. So in order to get our d is 1 over 600,000. Again, we know our n lambda is equal to d sine theta. What we're trying to find is our theta, right? We're trying to find the angle in degrees. We know our n is 2 because we want the angle between the central maximum and the second order maximum. So that's in between n is equal to 0 and n is equal to 2. Again, we know our wavelength is equal to 532 times 10 to the negative 9 meters. And now plugging in our numbers, we get 2 times 532 times 10 to the 9. Is equal to d, which is 1 over 600,000, times sine theta. And therefore, 2 times 532 times 10 to the negative 9, all over 1 over 600,000, is equal to sine theta. And therefore, our theta is the inverse sine of all of this. And this gives us an angle of 39.7 degrees. There we go. Renee wonders whether it would be possible to use a diffraction gradient to create a laser light show, where a blue laser light with wavelength 460 times 10 to the negative 9 meters creates a pattern that overlaps with a pattern created by a red light laser with wavelength 690 times 10 to the negative 9 meters. Explain what the complete pattern would look like. In your answer, you should calculate the number of maximum for the blue light, calculate the number of maximum for the red light, explain why there will be a limit of number of maximum for each laser light, show that one of the red maximum is the same angle as one of the blue maximum. So a reason why there's a limit to the amount of maximum that can be seen is because if we imagine our light going through a diffraction grating right here, and then obviously spreading out like so, we can see that once it gets to 90 degrees, like so this angle right here is 90 degrees with this line over here, it cannot go past 90 degrees, right? This light isn't going to go like, it's not going to go like that, is it? It's just, so the maximum angle is 90 degrees. And so obviously that's why there is a limit to the amount of maxima that can be seen. And so to calculate the number of maxima, we can again use our trusty n lambda is equal to d sine theta. And if we set theta to 90 degrees, that will give us the amount of maxima. So let's do that first for the red light. In order to see the maximum amount of maxima, we want to find our n value. And let's say, for example, our n value is 4. This is just an example. This is not the answer. All right. If our n value is 4, what that means is that if we go through our light, we have central maximum, and then 1, 2, 3, 4, and then 1, 2, 3, 4. Those are supposed to be evenly spaced. Just imagine they are. Okay. And so we have 4 orders of maximum on each side. And so what that means is that we have 9 total maxima. Right? We have the central one, and then we have 4 on each side, which equals 9. And so for this calculation, we want to rearrange for n, so we can find our n value and then do double plus 1. So double for the other side, and then plus 1 for the middle one. So we know that n is equal to d sine theta all over lambda. We know that our d is 1 over 600,000, which we found in the previous question. Sine theta, which is just sine 90. Now keep in mind, sine 90 is just 1. So if you want to simplify your calculation, you can just get rid of it, because anything times 1 is just itself. But I'm going to keep it in so you can see the full working. All over the wavelength, which is given up here as 690 times 10 to the 9. And that gives an n value of 2.42. Now 2.42, that means our maxima is 2, right? 0.42 means that like it's halfway through. And if you get a decimal value like this, you always round down to the nearest whole number. So even if it's like 3.99, you always round down to 3 because it's not quite 4. And so based on that logic, we round down to 2. And so what that means is that we have our central maxima and then 2 order of maxima on both sides. And so as you can see, we have 5 total for red. And so we can do the same exact process for the blue. Again, we know our n is equal to d sine theta all over our wavelength. D is 1 over 600,000 times our sine 90 degrees all over our wavelength, which is 460 times 10 to the negative 9. And that gives us an n value of 3.62. Again, we always round down to the nearest whole number, so our n is equal to 3. And so what that means is we have our central maxima and then 3 maxima on both sides. Again, in reality, those are evenly spaced. And so as you can see, we have 7 maxima possible. So if we look back at our checklist, we have calculated the maxima for blue, calculated the maxima for red, and we've also explained why there is a limit to the amount of maxima. Now we need to show that one of the red maxima is the same angle as one of the blue maxima. So the way we do that is through simultaneous equations. Again, we know that n lambda is equal to d sine theta. Our d is going to be the same in both cases because we're using the same diffraction grating. And because we're interested in finding the same angle, our theta is going to be the same in both cases. The only thing that's different is going to be our n, which is the order of maxima, and also our wavelength, because blue and red light have different wavelengths. And so we can get nr times lambda r for our red light is equal to d sine theta, and nb lambda b is equal to d sine theta. Again, these are the same because our diffraction grating is the same, so our d is the same in both cases, and we are interested in finding the same angle, so our sine theta is the same in both cases. So because both are equal to d sine theta, we can make them equal to each other, so nr lambda r is equal to nb lambda, and therefore nr all over nb is equal to lambda b all over lambda r. Now we are given the wavelength of the blue light and the wavelength of the red light, so we can make that substitution. So nr all over nb is equal to the wavelength of the blue light, which is 460 times 10 to the negative 9, all over the wavelength of the red light, which is 690 times 10 to. Now if we plug that into our calculator, we get 2 over 3. And so what that tells us is the third blue maxima is equal angle to the second red. Alright, so yes. Okay, question 3. The speed of sound in air is 343 meters per second. James attaches a buzzer to the end of a piece of string. James whirls the buzzer above his head in a horizontal circle of radius 1.02 meters, in a constant speed of 16 meters per second. Sabina stands at a long distance away and listens. Does that say Sabina? I think it is. Whatever, we're moving on. We're going with Sabina. Describe the motion of the buzzer when Sabina receives sound waves with the shortest wavelength. So, put simply, the shortest wavelength that she's going to perceive is when the buzzer is going directly towards her. That's all you need to learn. If the frequency emitted by the buzzer is 512 Hz, show that the lowest frequency heard by Sabina is 489 Hz. So this is a simple Doppler calculation where our f prime is equal to the frequency of the source all over the velocity of the wave plus or minus the velocity of the source. Now we want the lowest frequency, and so we want a plus in this case, right? And so plugging in our numbers, we know that the frequency of the source is 512 times the velocity of the wave. The wave is sound waves in air, so the speed of sound in air is 343, as given above, all over 343 plus 16. The reason why it's 16 is because we're given 16 meters per second right here. And this gives us a frequency of 489 Hz. And as you can see, that is the frequency that we're trying to find. Sabina stands a very long way away from James and listens to the buzzer. The sound appears to be increasing in frequency as the buzzer travels from point C to A. Explain why Sabina hears an increase in frequency from point C to A. You may want to use calculations to assist your answer. Whenever it says you may want to use something, you definitely want to use it, otherwise you'll lose points. May means you definitely calculate. So if we look at the buzzer at point C, right here, the buzzer is going like this, and its velocity is directly that way. And so the velocity component is directly away from Sabina, right? It's in the opposite direction. Sabina is this way, and the velocity component is that way, so it's in opposite direction. And so this is when Sabina will hear the lowest frequency, which we just calculated as 489 Hz. Now, just to be safe, calculate it again. All you have to do is just copy your working. It's not a big deal. At point B, the velocity is pointing in this direction right here. And so the buzzer is neither moving away or towards Sabina. And so at this point, Sabina will hear the actual frequency because the Doppler is all about relative velocity. And the velocity in this case is not facing towards or facing away. And so it's just the true frequency, which is given to us as 512 Hz. Now for A, this is the opposite case to C, where our velocity is facing directly towards Sabina. And so in our Doppler equation, where we have S times VW all over VW, this is where we have our minus situation. And so we can calculate that as F prime is equal to the velocity of the source, which is 512 times 343 all over 343 minus 16. And that gives a frequency of 537 Hz. And so at point A, the frequency heard by Sabina is 537. And so based on this, we can see that this is the frequency at point C, this is the frequency at point D, and this is the frequency at point A. And as you can see, as the buzzer goes from point C all the way to point A, the frequency is constantly increasing from the lowest over here to the medium and to the high. James and Sabina want to hear beats. He puts a second buzzer, which is also emitting a sound of 512 Hz, on the ground. James again swirls the original buzzer above his head, but at a different speed. When the buzzer is at point A, James lets go of it, so the buzzer flies off towards Sabina. Sabina hears a 10 Hz beat. Calculate the velocity of the buzzer at the point of release. So if we bring our situation back, the buzzer is released at point A, and we also have a second buzzer right here. That's our second buzzer, which is producing a frequency of 512 Hz. This buzzer over here is being released, and so therefore it's going to fly directly towards Sabina, and the beat frequency is 10 Hz. So, as this buzzer is flying towards Sabina, Sabina is going to experience a Doppler shift. So even though this buzzer is emitting 512 Hz, due to the Doppler shift, there's going to be beats heard, right? Because this has no relative velocity, it's just standing still. So Sabina is going to hear 512 Hz from this buzzer, but she's going to hear a higher frequency from this buzzer because it's moving towards her. And that's what we're trying to find, the velocity at which this buzzer was released. So we know our beat frequency is 10 Hz, and so our beat frequency in this case is the difference between F prime, which is going to be this frequency right here, so that's the frequency due to the Doppler shift, minus our F. And so our F is our true frequency, which is 512. Right, and the reason why we use these lines here That just means absolute value. And so what that means is that we always get a positive answer because the beat frequency is just the difference in the two frequencies. And so we know that f prime is equal to fs times vw all over vw minus vs, because we want the minus because it's going towards Sabina. And therefore we know f prime is equal to the velocity of the source, which we know is 512, times the velocity of the wave, which is 343, all over the velocity of the wave, 343, minus vs. Vs is the value that we're trying to find, right? The velocity of the source, which is this right here. And so plugging that into here, we get FB, which in this case is 10 hertz, right? As given up here. So 10 is equal to 512 times 343 all over 343 minus Vs minus our F, which again, as stated previously, our F is just the frequency of this buzzer, which is 512. And so now we need to rearrange for Vs to calculate our answer. Right off the bat, we can plus 512 on both sides, and we get 522 is equal to 512 times 343 all over 343 minus Vs. And then we can swap these two values around, and we get 343 minus Vs is equal to 512 times 343 all over 522. So moving this to this side and moving this to this side, we get 343 minus 512 times 343 all over 522 is equal to Vs. And this gives a source velocity of 6.57 meters per second. There we go. And with that, we are done.